Hello and welcome to Shape the System, where we find and tell the stories that help people to rethink the way the world works. We interview people from all over the world who are helping to change our systems for the better. Shape the System is an independent podcast with support from KPMG High Growth Ventures, who help ambitious founders and their teams scale up for success. More about KPMG High Growth Ventures after the interview. We hope you enjoy this episode.
Welcome everyone back to the episode of Shape the System. We're coming into our 5th year, which I'm pretty excited about, and we're nudging 100 episodes. So I think this is like episode 98 by the time it comes out, which is kind of exciting. And to be honest, we actually haven't talked that much about wind. And that's surprising because we talk about a lot of energy related stuff, and wind kind of never got a Guernsey. And today we're going to be talking to Nick Hodges from a company called Halcyon with an H. And we're going to be talking a lot about wind, which I'm pretty excited about, but I'm also super excited about the part of the spectrum we're going to be talking about, which is not large scale wind, which is kind of what gets all the press, but the other complete opposite end of that spectrum. So plenty of time to dive into that, and we will get into that. But Nick, before we do that, welcome to the show. But also before we talk about Halcyon, before we talk about, the context and the problem like we always do, just tell me a little bit about how you arrived to be working on Halcyon in the first place. What's your arc of a story here?
Yeah, it's an interesting story I never would have really thought of, but I have someone here who they are very engineering focused, but they're also very entrepreneurial focused. So they ask themselves, do I study business or study business and then learn engineering, or do I study engineering and then learn business? And he chose to go to school for engineering and learn business. I chose to go to school for business and learn engineering. So
right.
Going all the way back, I had a neighbor who was coming over all the time, and his favorite show, believe it or not, was The Walking Dead. I don't know if you know what that is. It's a old school zombie show. It's not really my thing.
The guy with the chainsaw in his arm? Is it that one?
Maybe. I think the one you're talking about is a little older, from the 80s. This is the TV show, but basically the same concept, post-apocalyptic world, and zombies aren't really my thing, but really struck me was how dependent modern society is on electricity. Mm-hmm. Basically, if you don't have electricity, you can't participate in modern life across the board. We wouldn't be talking here. No internet, no TV, no YouTube. I mean, when the power goes down at our house, my kids lose their mind. It's like, going back into the Stone Age. And even I find myself, sitting down to do something just instinctually, but you can't because there's no electricity. So I remember there was an episode where somebody got a hot shower, and it was just this life-changing thing within the show because they haven't had a hot shower in years. So that really struck me how dependent we are on electricity. So I started looking at what's called distributed energy for my house. So solar panels, for instance, be able to produce electricity at the structure that's being consumed at. And if you want solar panels, there's tons of great options, tons of great manufacturers, constantly redesigning, driving those costs down. Even 5-10 years ago, if you wanted storage batteries, there's good options. Now there's way more. But you go through any town or city, you're likely to see solar panels on a roof somewhere, whether it be a home or a warehouse, but you'll never see wind turbines. And kind of why is that? Because a complete distributed energy system, you got to have all three. You got to have solar panels for when it's sunny, wind turbines for when it's stormy, then battery power to store that energy for when you're ready to use it. So you've got two kind of taken care of, but the third one, when it comes to distributed energy for towns and cities, is completely non-existent. And there's a lot of good reasons for it. If you live, in the middle of here, somewhere like the Midwest, Oklahoma, Kansas, nothing but flat cornfields, you got 500 acres, put an open 3-bladed wind turbine on top of a 50-foot pole and you're good to go. I'd imagine it's similar in Australia. You got a lot of open land in the middle. And I think even on the coast a bit too. So good for open bladed if you're not living in town. But as soon as you get into town, wind starts whipping off of buildings, houses, roofs. And it's actually really bad for the traditional 3-bladed horizontal axis turbines. It can cause them to whip back and forth and even shatter blades at high speeds. So you have something like that in a city, like downtown Chicago, the Windy City, or somewhere on the coast there. And, you get blades breaking off and being thrown into crowds at high speeds. And it's just not a good thing. In addition to that, and it's not something you'd think of, but people don't like the looks of them. There was actually a news article from Australia that I actually used in one of our videos We're raising money right now on something called WeFunder. It's a regulation crowdfunding raise. I actually took a clip from a news article in Australia where a guy put up a huge, not even huge, but just medium-sized open-bladed turbine in his backyard. People lost their minds over it. Called the city, tried to get it taken down. I mean, they're not something that people want around them. So I kind of had that same experience looking for wind energy for myself, and didn't like any of the options. You can buy a wind turbine on Amazon or whatever for $100, but nobody does. And so I started looking for something that I liked better, and I couldn't find it, so I built it and rebuilt it and rebuilt it and rebuilt it. The first one was horrendous. Good idea. Horrendous execution, but eventually got to a place where I kind of liked what I had. It was starting to prove out the concept and showed it to people, and they kind of went nuts for it. It was kind of, I think there's a lot of people in the distributed energy space who I think feel like something is missing. And when they see this, they kind of go, that's the thing that's missing. That's what I need. That's that third piece. We got solar, we got storage, but now we have something viable for wind in towns and cities. And so that's kind of how it started, all the way from sitting down with a buddy watching TV through, 10, 12 years figuring something out that, couldn't get on the market at the time.
Yeah, it's whoever said nothing good comes of TV. Clearly, there are exceptions. So we're going to get into what it does and how it works in a little bit. So I definitely want to jump to that. But what I want to come back to first is kind of, and you've touched on it a bit, but I want to understand the state of play, like in wind generated energy, because you sort of said, look, there's large scale wind generation onshore and offshore, but it's massive 3-bladed stuff away from people, and is essentially virtually no wind in cities. But what's the energy generation opportunity in cities? I'm trying to understand the state of play in the part of the stack of the energy problem that you're focused on.
Yeah, I mean, I think the kind of the push for energy independence and being able to generate, store, and consume power at the structural level, I think that's grown a lot in the last 20, 30 years. But almost all of it has been solar. There's good reasons. Solar is a great technology, don't get me wrong. A lot of people live in places where it's sunny. But the other side of that, again, is wind energy. And there's just not a lot of wind turbines out there for people who live in towns and cities. Again, if you live in the country, you've got some options. But even then, people don't generally put them up. I think I've seen only a handful within 100 miles of where I live. So people have been actually trying for quite a while to create something for urban areas, and kind of the future as it is being prognosticated by the experts is something called vertical axis wind turbines. That's where the axis of rotation points up into the air. So instead of the axis pointing towards you and blades spinning like in a circle facing you, it points up into the air. So when you look down, it's spinning. And that's kind of considered the future, because it handles the issues with turbulent wind, changing directions a lot better. You still run into the issue, though, where it's called visual pollution. People don't want to look at it. Even if you have something funky, like I can never remember the name of them, but the Surveus serpentine ones or whatever.
We'll find a link.
Yeah, they look like DNA spinning, helical axis. There's usually 3 of them. Yeah. Even those, they're not making a lot of progress. There's a company in Iceland called Icewind. I think they have a great product. But even then, you run into that issue of visual pollution where people don't want to put it on the roof. So there's kind of a separate field that's very young, it's very immature, but it's called shrouded turbines. So shrouded turbines themselves, I guess, are nothing super new, but applying a shroud to a vertical axis turbine specifically for generating wind energy in towns and cities, that's what is new. There's a few companies trying to do it right now. We're obviously one. We're probably a couple years away. We are just finishing. So for the past few years, I've been working on this design, and kind of last year, I kind of felt like, this is it. This is the final model. This is what I've been looking for the past, 5-10 years or whatever. And so I brought it to an engineering company here in Salt Lake City, Utah. They're a multidisciplinary engineering team. They do products from idea to commercialization. They've done medical devices, they've done consumer goods, and some gear that went into the F-35 fighter jet. And so they are basically taking that design and mathematically optimizing it, figuring out how many vanes, how many angles, kind of the creative engineering is over. Now it's the mathematical optimization. So that's coming up here in April. And after that, it's probably 18 to 24 months. But there are two other companies, Aeromine and Ventum. They have similar concepts of a vertical axis shrouded turbine that they're trying to get to work as well. And just really cool stuff, in my opinion. I like both of their models. I want to say that I can never remember which one is which off the top of my head, but I'm gonna say Aeromine is from Texas here. Theirs is only single directional though, so you put it up facing west, and it only generates power facing west. And then I want to say that Aeromine is out of the UK. I want to say it was like a 25-year-old design even. It's just when they made it back in the 90s or whatever. Actually, 20 years wasn't even the 90s anymore. We're getting old, but they shelved it because no one cared. It's just the world wasn't ready. That kind of the feeling of an idea whose time has come. There's nothing more powerful. It has a good idea, but its time hadn't come yet. It has now. So they're dusting it off the shelf and putting it back on the market. So it's kind of a new area, but it's developing for sure.
Yeah, so I want to get into some of the engineering of it and how it works and what it does. But I want to come back to something that you just you didn't specifically say, but I want to understand it a bit more. You kind of prefaced right up front that when you're looking for energy security, you've used this term a few times in the last 10 minutes that we've talked, and that's obviously not, if not the top goal, one of the top goals. There is a need to generate energy from sun, generate energy from wind, and then store it. And often I'm hearing from people who are like pushing back on renewable and saying, we've got to go to nuclear and, whatever argument they're making. They're often saying, well, when the sun doesn't shine and the wind doesn't blow. But what I'm curious to understand purely from a weather perspective, how much of the time in general terms is neither the sun shining or the wind blowing? Are these two things tend to be like, if the sun's not shining, often you've got weather events that mean that you do have wind? Like, well, how does that look?
Yeah, I'll do my best to answer your question directly, but you actually touched on something that I think is really important, especially for Aussies. And specifically, the question you're asking is for solar. They have, I guess, websites where you can go online and look at your solar score, looking at your average power production per day, per year, how much you could get if you filled a certain space. With wind, it's not as, I guess, well-traveled because there's just a lot more solar companies out there. So a lot more has gone into kind of mapping the value of solar. But every city, every area, you're going to have an average hourly wind speed. And that average hourly wind speed is usually over a year. So if it's, I'm going to show my American here, 12 to 20 miles an hour, that's your average hourly wind speed. But you can get several days where you're not going to have any wind for sure, which is why, again, battery storage is that critical component. So you can generate a lot of power, say over, a 3-4 day period. Where here at my house, it's been crazy stormy and windy for the past week. But the next 2 days, the wind might not blow at all, but it might be sunny. Why you got to have all three. But to take it one step further, what you're talking about is why people who are sour on renewables in general, and they have honestly some cases in the sense of, there are days when it's not sunny or it's not windy. And if that lasts for 2-3 days, your battery system will probably run out, which is why there's something called baseload power. That's your utility power, providing basically the, 80-90% of power needs for a city. But I think what you're talking about is nuclear. Australia has the largest uranium reserves in the world. And if someone were to live be born today and live 80-90 years, they would basically generate enough nuclear waste to fill a soda can, and that's it for their entire life. And we can recycle about 80% of that, is my understanding. So think of a world where there is no coal power plants, there is no gas power plants, there is no emitting power of any kind, but you have baseload nuclear energy, recycling 80% of it. But then the structures themselves in cities are power plants. So every house is generating power through solar panels and wind turbines, every business, every warehouse. So you're not just, because there's a lot that can go wrong between the power plant and a home or a business as well. But if every structure was generating its own power through what's called distributed energy produced at the point it's consumed, that in conjunction with zero emitting utility scale baseload power, I think that's the future. I think 80 years from now, when you and I are thinking about retiring, kind of that's
126.
Yeah, that's right. Just starting to slow down a little bit. Yeah. Think about how to enjoy your final 40, 50 years. Yeah. I think, if that were to happen, I think that would be an amazing thing. And this wind turbine is kind of positioned to be part of that rooftop wind element of that future. And I think that's what's really exciting to be a part of.
Yeah, and if I'm going to try and wrap this, and we'll move into the how the product works. But fundamentally there has to be a broad energy mix for the whole thing to work, and a lot of the energy mix has to be always on, combined with generation coming from renewable sources to have zero emission. And some places lend themselves incredibly well to having large-scale solar or large-scale wind, but energy security comes from also having the ability to have small-scale solar and small-scale wind and, on-the-site storage. And these systems all working together. And when you look at the broad spectrum market, you say, look, whilst I'm never expecting small-scale wind to produce all the energy we ever need, there's absolutely a need for it, and it's the least serviced market. It's the one that's massively overlooked, and it's been done most poorly over time. In fact, that's why there's so little of it. Am I kind of summarizing pretty well?
Yeah, I mean, just the amount of people who have reached out, and individual homeowners all the way up through Fortune 500 companies, international conglomerates, billion-dollar companies. They're looking for what you're talking about, kind of that piece of something that isn't there.
Beautiful. All right, cool. So it sounds to me like there's going to be two fundamental challenges with making this a reality, whether you're doing it or someone else, but we'll obviously talk about in the context of Halcyon. The first of those is the engineering and the product and the design, and the second is the economic reality. Where would you like to start?
Engineering, always. Money is great. Engineering is better. Yeah.
So help me understand what happens. My understanding with large-scale solar is that the turbines are getting bigger and bigger and bigger because of the efficiencies that come with that. And so clearly if you're going in the other direction, you're swimming upstream for that general idea. What's going on there from a physics perspective and engineering perspective?
Yeah, I mean, from a physics, engineering, and even economic perspective, what you're talking about is correct. The equations that govern power output for wind turbines are heavily reliant on sweep area. So it's basically how long the blades are and the area that they operate in. There's a maximum efficiency that you can have. It's referred to as Betz's limit or Betz's law. And I cannot remember the decimal place, but it's about 59%, 59 point something, I think.
Something. Yep.
Yeah. So if you look at those giant wind turbines on top of a hill, they've had tens of millions, if not hundreds of millions of labor hours have gone into making them as efficient as possible. And they're about 50%. It's about as good as you can get. If you were to get one yourself for your own home, because, we're not engineers spending, $5-10 million on a turbine, you'd be looking at something probably closer to high 30s, maybe low 40s. The future of kind of distributed wind, especially in towns and cities, we mentioned, is the vertical axis turbines. Right now, they're about 20. You can get some in the 30s, just depending on the design and the size, but generally around in there. They're supposed to get up higher, as the theory, up into the upper 30s, maybe lower 40s, but they're just not there yet. But in terms of how it operates, our turbine is never going to be as efficient as an open three-bladed turbine on top of a hill. Never.
Right.
That's why you don't see those in towns and cities. But what we're trying to achieve is basically take a disadvantage and turn it into an advantage. So we mentioned that wind will bounce off of walls of houses and office buildings. That wind, some of it goes to the left, some of it goes to the right, but some of it goes up. And so if you have a 3-4 story building, like an apartment or a large warehouse, that wind is going to accumulate, going up and up and up every, 5-10 feet, more wind is hitting it. And then when it crests over the top of the building, it's going to hit that unobstructed wind coming over, and it's going to push and bend and go over the roof. And that's where we put our turbines. And there's an enormous amount of power in the wind coming off of that wall. And so what it does basically catches it and funnels it into the blade on the inside of it. So the blade is contained. You can't see it, or can't see it very well from the outside. You also can't really touch it unless you stick your hands up inside of it. So that's the safety and the visual aspect. And then what it happens is you build up an area of high pressure below the blade. And then the way that the wind moves above the blade, it's been kind of specially designed to create an area of low pressure above the blade. It's a concept of lift. Every airplane has it. Even the blades on the open bladed turbines have it. It works differently, obviously, but it's the same principle of creating an area of high pressure, area of low pressure, and putting the thing in between that you want to do the work, whether it's an airplane wing or a wind turbine blade. So that's kind of the design behind it. That's the design of the purpose of using the roof. So instead of it being a negative that will shatter at a open three-bladed turbine, it actually helps generate more power. And you can do that on the side of a house. You can do that on the side of a warehouse.
And so it's just fascinating because I didn't understand this part about it. What you've essentially done is said the context that we're operating in is buildings in compacted spaces, and that creates wind that works a certain way. And so how would you optimize the bit of kit and where would you put it to be able to tap into that type of wind, which you just wouldn't get in an open field?
Mm-hmm. Yeah, exactly. Because we're not going to compete with the open three-bladed turbines in the middle of nowhere. Your best bang for your buck is always going to be the cheapest way to generate the most power, and that's what those horizontal three-bladed turbines are. But in the city, can we figure out a way to turn kind of a harsh environment into something that works for the owner of the turbine and not against? And kind of that's where we are. So if you have a peak roof, you kind of put it on one side of the peak, so all the wind coming up the other side of the roof would hit it. And same with the flat roof building as well.
Yeah, and then kind of we're using, and I say we because I'm thinking of, you're also using it as we talk, this idea of out at an open field versus in the city versus where it's unsightly. Like I live in the Blue Mountains, an hour and a half from Sydney. It's a national UNESCO listed whatever. There's clearly never going to be a wind turbine anywhere near here. So if I ever want to leverage wind, and it actually gets fairly windy up here, what I'm doing is the only option. But even if you go 100 kilometres further west and you're out in open plains, you're no longer in the Blue Mountains National Park per se, but even these parts of the world, they're what we would call rural residential, right? There's people who are choosing to live out there not to be farmers. They're living out there because everything's out there, right? So I think even in that context, there's still a lot of pushback, at least we're seeing in Australia, because of this. There's parts of kind of California where you're driving from California across to Arizona where you go through past Joshua Tree National Park and you come into these open valleys, and there's no one really lives out there. There is some people who live out there, but there's certainly there's no farming out there. These places are deserts or semi-desert, but they have huge amounts of wind farms, and it's kind of entrancing in a way, but you would argue it hasn't made the place look nicer. I don't think anyone says that it's adding to it. And so it feels to me like the opportunity isn't so much can we compete with wind, it's more that there is a whole bunch of places where we're never going to have wind, right? And if we're never going to have wind, but there is wind there, then we're missing an opportunity to be able to leverage that wind to supplement what we're doing. So if we switch from kind of the physics and kind of the engineering challenges, and you talked about efficiency, that might be at 30% instead of 50%, looking at in terms of pure energy efficiency is one thing, but if you have to make a comparison, you have to make an economic comparison. If you spend $1,000 on per every $1,000 spent on a 50-foot wind turbine versus every $1,000 spent on a Halcium unit, like how do the efficiencies stack up then? Like what's the cost of energy production? Help me understand that aspect.
Yeah, so I mentioned optimization is what we're doing right now. So the engineers have kind of taken my design and they're kind of running with it using their experience and computational fluid dynamics to redesign it. So when we talk cost, we're talking kind of about pricing something that isn't finalized yet. But if you look at kind of the size and what it's made out of and the most expensive components, which right now is absolutely the generator, we're looking at $1 a watt sold wholesale, and then usually an installer will install these. Generally speaking, not a lot of individuals are putting their own solar up. Some do, don't get me wrong. A lot of knowledgeable DIYers out there, but for an installer, it'd be about $3 a watt, which is about what solar is, at least here in this country. So if you get a 10,000 watt system, that'd be about $30,000 installed. And so that's what we're shooting for, is basically from a financial perspective, it's not going to be like, do you want to put on, $10,000 worth of solar and get the same amount of power as, $40,000 worth of wind. It's just if your budget is 10,000, how do you want to mix and match that between solar and wind? And that's kind of the goal.
Yeah, like, I mean, if it'd be very, just purely from a go-to-market perspective, if you can say hand on heart to a customer, you're basically at price parity with regards to cost per watt of output. And it would obviously depend on, well, you live in a windy place and there's no sun, clearly that's your decision. But if you live in a sunny place with no wind, well, then clearly mix and match appropriately. When you think about what's happening in a city, and I'm talking about a built-up area of a city like downtown, not so much a suburb, is solar at a disadvantage in terms of to really leverage the solar you're on top of a massive building? There's not enough space up there, or there's going to be shadow. Like, what's the reality for solar in built-up areas?
Yeah, so I mean, you kind of run into two things. What you're talking about with shading, I was actually talking to an installer here, and he said it was some astronomically high figure. I want to say it was 50% of people who want solar can't get it. I feel like that's too high, so I'm just going to tell you it's like a third or 25%. Just because their roof doesn't face the right way, or they have a tree in the way, or just something that doesn't work out. But kind of the beauty of distributed energy and the beauty of this design with solar panels is that it's not competing with solar panels for roof space. So you guys in the southern hemisphere, you guys put solar panels on the north-facing roof. Kind of the south-facing roof is worthless when it comes to solar panels, but that's where our turbine would go. Similar with flat roof buildings, you put solar kind of in the center and there's a lot of room on the edges, and that's where our turbine goes. So it's made to work really in conjunction with solar. So not necessarily that one will be at the advantage or disadvantage of being in the city or not, but how do both work together regardless of what your circumstances are? And I think that's kind of the beauty of the solution.
Yeah, it's it's fascinating. And I want to get to the visual aesthetic part of it in a second, but I kind of want to, like, we've had a few chats, and I'm trying to remember the name of them. It's a Novi Ocean, I think was the name of the product. Was hundreds ago. We interviewed a couple of years ago, and they were talking about a tidal energy production and unit. It was a fascinating unit that basically was able to make energy in both movements of the water, not just the upward movement, somehow it's cycling water back through it. And we spent probably 5 minutes talking about the engineering because it was interesting, but he spent most of the time talking about how these things can be made with massive amounts of existing engineering stack and existing kind of componentry. And that economic reason was actually the thing that was making this cost competitive. When you make the first 20 units or the first 200 units, you're having to use 3D printers and you're having to do short runs, and tooling is an overhead that has to be amortized poorly. But if you kind of strip that away and say, at the point where you're doing 10,000 or 100,000 of these units, like, where you see these unit costs getting to that will reflect truly the scale that you're competing with, if you think about not competing with, but comparing to being solar.
Yeah, the goal is, $1 a watt, $1 to $1.50 watt produced. So if we get down to $1, we'll be at parity. If we get $1.50, if you 3x that, that's $4.50 a watt. It's a bit higher than solar, but it would be one of the more cost competitive. And the reason is we're basically what you're talking about earlier, trying to upsize it to make it as big as possible and take advantage of kind of how wind operates in towns and cities as much as possible to generate as much electricity as possible per cost. So in terms of like the beautiful brilliance of engineering, it's very, like, some of these concepts have been around for hundreds, if not thousands of years. Kind of stole something called from a lot of different places, don't get me wrong, but in the Middle East, they had these things called wind catchers, and I forget the Farsi name for them, but they're these giant towers that stick up in the air, and they were air conditioners, and they would cool a house. You could have 100-degree days and have it nice inside the house because of these wind catchers. And they would even pair them with underground water to keep basically ice frozen at near freezing, be for you like 1 or 2 degrees all the way through the summer even. So kind of, if you look at what we have, it looks like kind of like one of those or similar principles. So you're talking about kind of time-tested principles that have been around. Kind of the novelty of it is, though, taking these different principles and recombining them, repurposing them for the purpose of creating wind energy with turbulent wind within towns and cities. So that's kind of the simplicity, but also beauty of it is that it is theoretically simple, and simple is, from a manufacturing and performance standpoint, much better than complicated.
Yeah.
Not from the German perspective, maybe.
Is there, like, I guess the thing that I'm trying to kind of understand is, like, like at what level of scale does this become, does the economic viability kick in? In some cases, people like, until we do 200 small, medium, SMRs, like the modular reactors, we just can't get the thing to work. But in your case, it's sort of saying these things aren't going to get much cheaper from the 2,000th unit to the 200,000th unit because you're already at scale, because this is well understood.
Yeah, I guess you're talking more about like negotiating with manufacturing. Kind of, again, the materials that we're using are not novel, neither manufacturing processes. So, but they're large units. So smaller runs would be more fine than, if you were to do small runs of like a toy or something. But basically, out of the gate, we're hoping for anywhere from $1 to $1.50. But you're not talking about scale and size. You're talking about scale of manufacturing, but scale and size, too. You just get to a point where there's too much material. There was a shrouded wind turbine, not that we like to be associated with them because they went bankrupt, but there's a shrouded turbine. They built one in China. It was it was absurd. It was like 80 feet tall, I want to say. It was massive. It was made out of steel. I think probably cost millions of dollars to make. You're never going to get that back.
Right.
So, something small for a rooftop on a house, a little bit bigger for a rooftop on a business. That's not the right size. Any bigger than that, there's just a lot of material.
Yeah, okay. Interesting. And what is the material? Is this metals or polycarbonates or plastics? What are we using?
So you're going to have a metal structure for the inside for sure, and the outside I'm not sure about yet. We're looking at kind of biodegradable fiberglass. The issue is finding a balance between something that will last 20 to 25 years on a rooftop. You're talking sun, you're talking sand, you're talking salt, you're talking ice, but will degrade once it's, at the end of its life. So it's a little bit tricky to find a balance between those two things.
Well, like why would you want it to degrade?
I don't want to basically have 12-foot piece of plastic as a renewable energy source and have it never degrade. So that's kind of what we're looking at for sure.
Yeah, the only reason I kind of drill into it is we had Mike Smith from ZeroCo, and his argument was plastic isn't renewable, and that can actually be its superpower, because if you utilize it in a place where you don't want it to degrade, then you can keep using it. Now, he's talking about hand soaps, so you might have a different opinion because you're like, we need it to not degrade at all. The fact that it partially degrades over 2,000 years is actually problematic. Can you help me understand the degrade bit a bit more, because that's actually quite interesting.
Yeah, so I mean, plastic from a perspective of like durability, talking 20, 25 years on a roof. So it's going to wear at some point for some reason, whether it be sun, sand, salt, whatever the reason is. But at the same time, you don't want to produce, like if your mission is to change energy for the better, which ours is, don't want to, I guess, produce something that is never going to basically break down or come back from. So that's just kind of my thinking. It may be impractical from a cost or performance standpoint. That's the kind of the downside of degradable materials, is that they do degrade. So how do you find something that will last, again, 20, 25 years on a roof? From your perspective of never degrading, if you made something that was eternal, which would be kind of cool, but maybe not. Eventually, the generator on the inside, they're only rated for 20, 25 years before they have to be replaced. So
yeah, I mean, realistically, that's what everyone looks at with any of these, whether it's a large wind turbine or a solar thing or a battery in a car. Everyone's kind of aiming for 20 to 30 years of practical usage before it has to be in some way dismantled, recycled. There's a company we interviewed a couple of years ago, Rui Peng from Critical, and they make office furniture and office fit-outs with recycled plastics. And this stuff's super durable. And in fact, their business model is to sell it, and then they buy it back from you later and recycle it and remake it and sell it to someone else.
Yeah,
so
really cool.
It feels like some circularity that might be interesting here. Before we just move on to kind of where you're up to and where you're heading to next, and you touched on it a bit, just help me understand a bit more about the aesthetic thing, because ultimately, if it's not a big turbine with big spinning things that people don't find attractive, maybe for aesthetic, purely visual reasons, but potentially because it's associated with something that they don't find attractive. But ignoring that, how have you approached the visual design of the Halcyon box, the unit, like to not suffer from the same challenge?
Yeah, to be honest with you, I'm more of the math guy, not the artist guy, but I've been lucky to have a lot of artists around me. So kind of when we were developed the technical side, the functional side, made sure it worked. And then we had somebody come through, they were an industrial designer, and kind of reimagine it into something that looked a little bit better. Because what you're talking about, the visual pollution, we've talked about it a little bit too. It's enough to basically kill all wind power in towns if people aren't going to tolerate it being on a roof. So it was designed specifically to kind of hopefully improve the aesthetics of whatever structure it's on, or at the very least not dramatically detract from them. So there's no obnoxious spinning blades. It's designed to be something that is intriguing at the very least. For instance, when people see this, they love it. It was on a website, Euronews, for a little while.
Mm-hmm.
And the picture that was on there, it was one of their best performing articles for 48 hours, just because people see it and they really like the look of it. So we're trying to keep that through design so that when people see it, it's hopefully not something that they say, we're not going to put that on, it's too ugly. And hopefully it's the opposite. They think, this is something that's really going to, be part of the aesthetic of what we're going for on our company headquarters, on our school. We've had port operators reach out, like maritime commerce, whatever it is. Hopefully they're looking at it as something that would kind of enhance their architecture and not detract from it. Not something you have to hide, in other words, in the center of the roof. Something that you would kind of be proud to display on the edge. Like if you're a Whole Foods or, something where you have a mission statement for, kind of sustainability, something that you would want to put over the entrance to your grocery store, office, or whatever, to make a statement.
Yeah. I mean, we've had plenty of conversations in the last 4 years about the importance of brand. Just one of our interviews literally two months ago with Raz from Flowwater. And I mean, they're building and putting, just water bubblers, I think we call them in Australia. I don't know what you'd call them, but not a faucet, but like a thing that a school kid might use or you might have at a gym. And those traditionally are basically, soulless metal boxes that functionally create water coming out and usually don't work properly. And they saw the opportunity to basically say, we want someone to see one of these and be like, oh, that's a Flowwater. I love those. I know that the water's going to be great. And the brand represents it so that people say, hey, why haven't we got Flowwater at our school or our gym or whatever it is? And they understand the importance not only of good design, but creating a brand that people can kind of attach to and spruik and advocate for. What's interesting, I think, with where you're starting is that in the context of someone putting a massive turbine out in a field, the field is lovely, the nature is lovely. So anything you put in that environment, no matter how well designed, is going to look out of place and ugly and undesirable because of the context it's placed in. But when you look at a city that's modern and it's, got basically potentially ugly buildings and nice buildings, but you put something that is modern and aesthetically, pleasing, the curvature on these things, if you haven't, like for anyone listening, go and check out Halcium's site and go and have a look at these things. It's like, I would say it's like the Dyson of wind generators. I don't know if that's the right way for me to tell. Has someone said that to you before?
They have, yes. They said that we should use that in our marketing.
It's totally true. These things are they're kind of futuristic, but without being obtuse. The design's interesting, and as I think you used the word intriguing, but they're also I think they're respectful to the environment they're placed in. Interestingly, when you show them in a lot of your images, you show them in nature, which is ironic given that's not typically where they're going to show up. But even showing them in a building context, it looks to me like you're creating something that's designed to be able to make a statement by itself, but not be ugly, but also not be too competitive with the space that it's in, remembering that it's an office building and they have a brand, or it's a Whole Foods, as you said, and they have a brand. I find the design fascinating, and props to whoever came through with the design. I'm sure you'll keep evolving it. I've got a couple more questions. The first one, I kind of just want to understand, we talked about it before we turned the show on, but like where are you up to right now? Like what's the next big hill for you? Like what's the next big milestone? And just help me understand like what's challenging in that so I can understand.
Yeah, so I mean, basically the last few years, trying to, there's infinite possibilities of what you could possibly do for a shrouded vertical axis wind turbine. So basically went through all the infinite possibilities and settled on this last one. And that was last January, and then hired a third-party engineering firm to take over from there. So we basically did the creative engineering, and they're doing the mathematical engineering now. They're currently doing what they're referring to as optimization. So basically mathematically optimizing the design that we've handed them. changing the scale, changing the angles. Still, again, what you're talking about, being respectful of the architecture and the industrial design is what we refer to it as. And then once that's done, we'll build it and test it. And then basically after that, it needs to be mechanically and electrically engineered to last 20 to 25 years on a roof. And as it turns out, engineering is very expensive. So right now they're finishing optimization. That's all been funded. But the work after that, if we take that optimized turbine, build it, and it checks out, it's actually engineering it to make it manufacturable, installable, shippable, and whatnot. And so we're raising money right now on a website called WeFunder, wefunder.com. It's wefunder.com/Halcium directly is the link. And raising money towards that. And then also exploring other sources as well to basically try and take this thing, again, that came from two guys watching a horrendous TV show about zombies into something that, will fulfill the mission of changing energy for the better. And that's kind of where we are now. Yeah.
Yeah, and like very specifically, once you get over this engineering part that you said's funded, is the outcome from there that you've got a product that can then be bought? Or is it that you have a product that could then be ready to be starting to be manufactured and then bought?
Yeah, so the optimizations can be done at the end of April. That's when we'll have the designs, we'll build it, have the power curve is what it's called, all the output at any given wind speed, and then all of the underlying mathematical support for both optimization and the power generation. We then build the prototype to see if it functions even remotely close to what we're looking for, because usually your first prototype, it's a relatively low to moderate fidelity. And then from there, it has to actually be engineered, not just optimized, but how do we actually turn this into something that can be manufactured? So that's from the end of April, 18 to 24 months, about $2 million American. So that's kind of where we are now. How do I say this? I don't want to ever say that like there isn't a challenge ahead, because it is, but I think the most challenging part is finished. That is figuring out a design that will actually work. From there, it's just figuring out the nuts and bolts.
Execution.
Exactly.
I think I've said it a few times on the show. We tend to catch the entrepreneur in the company at its inflection point. So it sounds like we might be doing that again. So for anyone who is out there and is like interested in funding related stuff, wefunder.com/Halcium. That's calcium with an H. We'll put links in the show. I've got just one last question, which is kind of adjacent to it, but I was curious about it because I read it on the site. You had like a vision for long term or longer term for this to be manufactured and deployed and go to market in local markets rather than trying to be the builder for yourself. Just help me understand that aspiration a little bit more.
Yeah, I mean, it all comes down to changing energy for the better. Again, the mission of the company, I think, should kind of influence everything that you do. So there are a few different things about that. One is if you manufacture locally in the places that your product is being purchased and actually used, it's actually benefiting those markets, not just for the turbine existing, but those are jobs at the actual manufacturing, the places that they buy from across the board. Again, kind of the other thing is that manufacturing in China, I mean, forget about the political risk for a second for Westerners manufacturing in China at the moment, but you're going to manufacture probably some factory inland, going to be shipped from the factory to the coast, loaded from the truck onto a container, onto a ship, and then shipped across the largest ocean on the planet, unloaded again at port, and then shipped again from our warehouse to whatever consumer is using it. Or you can just produce it, next to the place that you're going to be shipping out of. And, again, the economic benefit as well. So right now, most of the attention is coming in the US. We're an American company. So I think naturally we have a little bit of an audience here, but Europe is, I think, probably going to be just as big, if not bigger. So we'll probably start here just because it's local. Probably manufacture in the US. And if we can't in the US, then in North America. And if not in North America, then, we'll go wherever we need to for whatever parts we can't do locally. And after that, I think it's the EU. Because again, if you're a German we have a lot of people from the Netherlands, actually. If you're buying an American product made in America and shipping it from America to the Netherlands, or you buy a Nederlander product made in the Netherlands by Dutch people. So I think that's kind of supporting the mission of changing energy for the better, not just how we produce energy, but how we actually consume energy and logistics as well. Yeah.
It's the man behind the bar situation.
That's right.
Yeah, I find it fascinating. And the reason why I think it's highly relevant is that, as you said, once you've got the engineering for this right and you've optimized that in from a pure testing perspective and then said, here's the playbook, here's how you build one, the actual act of building this thing that you now know works well and aesthetically is pleasing and it's clear how to install it is replicable. The idea that you have to be, a semiconductor manufacturer and there's $100 million just to buy one of the machines. And so it makes sense to have it centralized and distributed when you've got a large product that would cost huge amounts of money and energy to move it around, making it in where it's sourced because it's simple enough to replicate once you know how to do it, absolutely makes sense. I mean, I totally get it. Quite fascinating. Well, Nick, that's plenty for today. I'm really excited to have chatted to you. Hopefully we're being helpful and really excited to sort of check in over the next couple of years. I've been following you for a couple of years, so I'm hoping the next time I do, you're through the other side of it and I can buy one for whatever house I end up building because it looks like a fascinating product. But thanks for joining us on the show today.
If we do, it'll be because of you, Vincent. Appreciate you.
Excellent.
We hope you enjoyed this episode of Shape the System. As usual, if you'd like to suggest a guest, someone that you know who's helped change a system for the better, please go to www.shapethesystem.org, click on the top right-hand corner, then click Suggest Guest. Make sure that you click subscribe so that you get the new episode. Shape the System is an independent podcast with support from KPMG High Growth Ventures. Connects founders to the services they need along their journey. Whether you are looking to refine your strategy, mature your finance function, prepare for a capital raise, expand abroad, or simply comply with regulatory requirements, they provide you with the support you need to drive your business forward.